Hi, everyone. My name is Luofeng, and today it's a pleasure to introduce our work interference among first price pacing equilibria. This is joint work with a bunch of wonderful collaborators, Christian, Sergei, Okke, Liang, Nicolas, and Congshan. So Christian and Okke are also in the audience, so thanks so much for supporting me. Okay. So the problem our paper would like to address is that so in practice, people would like to run many A/B tests at the same time. And one particular way to run many A/B tests at the same time is what we call the cluster A/B test. So this is a diagram illustrating that cluster A/B test scheme. So first I model the marketplace as a bipartite graph. So on the left are the advertisers, and on the right, the orange and the green nodes, they are the items or the impressions. So in cluster A/B test, we segment the market into many smaller submarkets, and we hope that each small submarkets are a good approximation of the whole market. And then with this segmentation, we can run many A/B tests at the same time. So for example, one way to instantiate a parallel A/B test would be to treat one submarket as the test and the rest as the control. And there are also many other variations. And the problem we would like to address is that, so of course, there is no perfect segmentation, and there is always interference. So for example, the green nodes right here, they are attracting advertisers from across clusters. So the research question we would like to answer is, so what would the market be like if there were no interference? And in order to describe our method and our model, my talk is divided into two parts. So in the first part, I'll talk about the FPP model. And in the second part, I'll talk about how we formulate interference using the FPP language. So in the FPP, we have three inputs, BVS. So B is a budget vector. So it's one scalar for each buyer. And V is the value function for buyers. So for example, VI theta would mean the value of buyer I to item theta. And S is supply. It's a probability distribution supported on the item set theta. So we're going a little bit abstract here. We have because we have a continuous set of items. Okay. So now given these primitives, an FPP operates in the following way. So each buyer is assigned a pacing multiplier beta I. It's a number between 0 and 1. And for an item theta, the buyer will put a bid of this much, beta I times VI theta. So the role of beta I is to control the bidding process, because beta is a number that's less than 1, so it's effectively scaling down the bids. And in our models, the buyer will commit to that pacing multiplier. So the buyer will use the same multiplier for all items. And the items are allocated via a first price auction. The price is determined by the highest bid, and the winner will be charged by per bid. So the platform would like to know an ideal, a good configuration of pacing profile. So a good pacing profile should satisfy the following properties. It should be first budget feasible. It means that the buyers should stay within their budgets. And the second condition, no unnecessary pacing, is motivated from a budget management perspective. So it's saying that a platform do not want to pace the buyers if the spending is less than the budget. And if someone's spending equals to the budget, then we pace that that buyer. So at this stage, I've basically described all the conditions to define an FEPE. So now let me introduce a few more notations to make it more precise. So given BVS, a limit FEPE pacing multiplier is such that there exists a price function and allocations such that the following three sets of conditions are satisfied. So the first condition is first price condition. It's saying that the price is determined by first price auction, and if someone is being allocated something, then he will be the highest bidder. And the second condition is just the no unnecessary pacing condition. And of course, there are some other market clearing condition and feasibility conditions. There are a few remarks. The first thing is FAPE always exists and is unique. This is also mentioned in the previous talk. And another nice property that we use heavily in our paper is that FAPE has a convex program characterization. And I will talk more about this in a few slides. And FAPE is a centralized, static, hindsight solution concept. So there's a lot to unpack here. So we say it's a centralized because we're thinking from the platform's perspective. So the platform would like to figure out what is the ideal pacing configuration. So this is in contrast to other work that think from the bidder's perspective. So what's the optimal bidding strategy? That kind of perspective. So we're different in this sense. And FAPE is also a static and hindsight solution concept. So all the items are known in advance to the platform. So this is in contrast to, in reality, the items, they usually arrive sequentially. So it's another feature of FAPE. And in this work, we focus on first price auctions and pacing. There are other ways to manage budgets, such as throttling, but we won't talk about, but we don't deal with throttling here. And the revenue in the limit FAPE is defined by this integral. So it's essentially the inner product between the price and the supply. So it'll be the quantity of interest, and we would like to estimate revenue later. All right, just like any statistical model, we need a population model that describes the data generating process. And we also need the data, of course. And the finite FAPE solution that I'm going to introduce in this slide will be the data that we observe. So previously we defined limit FAPE on an abstract arbitrary item set. And a finite FAPE is really just a limit FAPE on a discrete set. And the probability distribution will be the empirical distribution. But in our definition here, everything is discrete. And so we can write everything out. And here I'm writing down the exact 3 conditions. So, and FAPE will be the model that we use to model the data we observe. In our previous work, we showed that the finite FAPE will converge to the limit FAPE according to some central limit kind of theorem. A few more notations. So we let beta gamma to be the pacing multiplier in the finite FAPE, and revenue gamma to be just the average of the price. And if the market satisfies certain regularity conditions, we show that we have the following central limit theorems. And the variance, we derive closed form expressions for the variance, and we are able to, we can estimate those variance using the data. And the tool we use to prove this central limit theorem is the following complex program characterization. So it turns out that FAPE is equivalent to the Eisenberg-Gale program. So it's a constraint optimization program. The constraint set is in 0 and 1. So this is consistent with the previous definition. And we also have this H of beta is a convex objective. They're equivalent in the sense that the FAPE is the unique solution to the Eisenberg-Gale program. And for the finite FAPE or the observed FAPE, the pacing multiplier, equilibrium pacing multiplier, also solve a sample analog of the Eisenberg-Gale program. So from here, we can see that FAPE is a very convenient tool because it's very applicable solution concept for ad auction platforms. And at the same time, it has this convex program characterization that where we can use tools from optimization and statistics to derive theorem and analyze the market equilibrium. Okay, so now we can go into the interference part of the paper. So just a quick recap of the motivation. We would like to run many parallel A/B tests at the same time, and we assume in our work we assume that a good segmentation of the market is given. So we assume the clusters are given, and based on that we develop our theory. And we assume each submarket is a good surrogate of the whole market, and we want to know what would the market be like if there is no interference. So just a graphical illustration of our formulation. So the left panel is the figure we just saw at the very beginning. It represents the interfered data we observe in practice. And the middle panel is the limit analog of that interfered market. And here are a few more notations. We use theta1, theta2, theta3 to denote the item sets in those submarkets. And they're supposed to attract the advertisers in their submarkets. And also I have this theta bad item set. It's defined to be the item that attracts advertisers from across clusters, from across submarkets. And on the right panel is the limit market without interference. So I basically just removed the bad item set. And remember that for each FEVE, we can write down a convex program characterization of the market equilibrium. So we can also do exactly the same for the three plus that we just saw. Let S be a distribution supported on theta1 to theta k, and let S prime to be a distribution on the the bad item set. And then the three markets that we just saw can be conveniently denoted by these three notations here. And each of them solve a convex program corresponding to that market. And now our research question can be formulated as we use the data from M alpha hat, and we would like to infer about the market without interference, which is the M0 market. And our approach is pretty straightforward. So we look at the map alpha to alpha star, beta star alpha, and we write down the gradient expression. We first define a surrogate, this beta tilde star, which is essentially taking one gradient step from the Hessian multiplier in the interfered market. And then we also write down its finite sample analog. Our theorem shows that this one-step gradient surrogate has lower variance, and we're able to estimate that surrogate with the usual statistical error. And in order to show the debiasing effect, we conduct a synthetic experiment. So we construct market with 10 buyers and 1,000 items. And then we vary the proportion of interfering items. The next thing we do is we compute the debiased estimate and the naive estimate that we directly observe. And then we plot them as a function of the alpha. We do see that the debiased estimate is consistently closer to the true parameter across all choices of alpha. So our procedure is straightforward, and it's working in this simulation. Yeah, and our work is currently on archive, and we also have a few works that's preceding our work. So yeah, I'm happy to take any questions from the audience.
Thank you.